Okay, so in other words, you use indefinite metrics in special and general relativity. And then finally, we have to distinguish between physics and mathematics. I don't know what mathematics is. It's something like the set of all consistent. It's the set of all consistent sets of consistent statements or something, something like that. And whereas physics is a true description of nature, and so you can have many theories that are consistent, but only some of them are right and describe this universe. Or Susskind's megaverse, which I think is a much better word than multiverse, by the way. So you always have to keep in mind that every now and then we get to change physics. And so, those are the exciting times, especially when the change is something understandable. Okay, all right, so let's see, where are my notes? Let's take a shower. By the way, there's a story, which I think is a true story, but it may just be a joke. Harry Hopkins was one of FDR's assistants, and he would often be an intermediary between Churchill and Roosevelt. And Hopkins was a heavy drinker, and so was Roosevelt. Roosevelt, no, but Churchill. And so Hopkins and Churchill got along quite well. And at one point, Churchill said to Hopkins, "Doesn't this water taste funny?" And Hopkins said, "Of course it tastes funny. There's no whiskey in it." I'm not urging you all to drink. It was just a joke. Okay, now an example of a Hilbert space. The space of square integrable functions, the inner product of f with g is an integral. Let us even say square integral functions defined on a finite interval. So that's the inner product. It's a gold standard. The norm squared, square of the norm is just the inner product of f with the integral of the absolute squared of f, and this in fact, so in other words, this the space in question is the vector space of all square integrable functions. So forth. Now, of course, there's something hiding under the term square integrable. Square integrable means that this thing converges to something finite. So this integral is finite on this interval. The other thing is, well, what do you mean by integral? This is a standard, simple definition of what a definite integral is, and then there are fancy definitions due to Lebesgue and so forth. So, I think, in fact, that the rigorous definition is the Lebesgue definition. But in any event, it's this space of square integrable functions on a definite interval is an inner product space. It's also complete, and it's a Hilbert space. And in quantum mechanics, we either have a finite interval, or we have an infinite interval, and I think, in fact, also in the infinite interval cases, a Hilbert space. Okay, now the case that you're worried about is this Minkowski space, and of course there you have an inner product of say the inner product of momentum with position, well, this is p vector dot x vector minus p0 x0, and so this is p dot x minus, and p0 is typically e over c, and x0 is ct, and so this is p dot x minus et. Of course, if you look at books on special relativity, half the time it's this way, half the time there's an overall minus sign. So it's depends on whether you want to use, you know, et minus p dot x or p dot x minus et. I think that this is the better choice because we have 3 plus signs and 1 minus sign, whereas in the other case you have 3 minus signs and 1 plus sign. And I'm not nuts about minus signs, so I prefer this one. But it's not a big deal. Anyway, this is an indefinite metric, obviously. All right, any questions? Yeah.
What makes that the Minkowski space, though?
Minkowski. Oh, it's just that Minkowski was a scientist who worked in special relativity. This baptism of names is I think it's actually kind of stupid, because when you give something in science a name, you name it after somebody. Well, that tells you nothing about the thing. It only tells you something about the person who gets the name, whose name is being used.
So you can look it up in an index.
Well, you can, all right, thank you. All right, you can look it up in an index. It would be much better to say, well, I don't know quite one word to describe this, but to call it an indefinite metric, I think is better than calling it a Minkowski metric. But I don't know. I mean, it's, who knows? All right, so I owe some people some candy. Let me see. How many do I need down back there? So let's see. You asked a question, right? You. All right, and you must have asked.
I'm fine, thank you.
You're fine?
I already asked your question.
Is that it? All right, the next topic is an important inequality. And, well, here I've labeled it the Schwarz Inequality, so I'm violating the rule. I'm just but what the hell, I'm just following what everybody else does. So, it's normally called the Schwarz Inequality. And one of the hardest parts of dealing with the Schwarz inequality, by the way, is spelling Schwarz, because there are so many different names and ways of spelling it. You can have a C or no C, you can end in a Z, or you can end in ZT, and I think this is the correct spelling for this particular mathematician. All right, the Schwarz inequality is simply this. The inner product of F with F times the inner product of G with G, sorry about my writing, is greater than or equal to the inner product of F with G, absolute value squared. And this is true for any Schwarz inner product. So therefore, since a positive definite inner product has all the properties, is also a Schwarz inner product, it follows for both the gold and the silver. So this is gold, silver. I must say I've gotten a lot of mileage out of your suggestion. All right, so I'm going to go through the proof of this. It's very simple, but it's a little tricky, especially the very first part where we just, all right, anyway, let me just say what it is. consider this, f minus lambda g, the inner product of f minus lambda g. And what are we assuming? We're assuming that this is a silver or gold inner product. And let's remember what the positivity condition is. For the gold kind, the inner product of any vector with itself is non-negative. The Schwarz kind, the inner product of any vector with itself is also non-negative. So we've got what I'm going to say here, namely that this inner product is greater than equal to 0 for all lambda, real or complex. And then this thing is ff minus lambda star gf minus lambda fg plus lambda squared gg. So I've used the hermeticity property and so forth. That is to say, this type, minus lambda gf, well, that gives you minus lambda star gf, because you're antilinear on the first member, linear on the second. Okay. Now, we first want to get rid of a certain special case, a special case where gg might vanish. So, if gg is 0, then what? Then we know that this thing is non-negative because we've got a silver gold in a product. And now, if this is going to be non-negative when gg is 0, so this term is gone, well, you can fiddle with these things, with the lambda and the lambda star, and it's pretty obvious that if this is non-zero, and it's the complex conjugate of that, so if this is non-zero, you can certainly make this thing negative by screwing around with lambda. Okay. So, if gg vanishes, this can only remain non-negative if fg is 0. But then if fg is 0, both sides of the Schwarz inequality vanish and the thing is true trivially. So the Schwarz inequality holds trivially gg vanishes. And now we can go to the case that's serious, namely when gg is non-zero. Okay. So now let's assume that gg is non-zero. Well then, what we do is we make a particular choice for lambda. We set lambda equal to the inner product of g with f divided by the inner product of g with g. You see, because we can assume that gg is non-zero. Okay. So then, what is this structure? Well, then this structure is, in fact, let me do this. I'll say it is this so that I can get to use this space. This thing is then the inner product of f minus gf over gg times g. The inner product with itself, in fact. Because all of these things were an inner product of a vector with itself. And now, if you multiply that out, you of course get ff. And now you get some nice cancellations. So you get, well, maybe I'll write them down explicitly and then do the cancellations. So you get minus f with g times g with f over gg. So that's this one with that one. And then the other cross term is this one. And so that is minus gf star over g GG times the inner product of G with F. And of course, this thing is the same thing as FG. So this is the same thing as FG. So GF star is FG because by the hermeticity property. And then the last term is plus GF star GF over GG squared times GG. Okay, well, if you work that out, what is it? One of these, first of all, you cancel this with one of these, and now you've got three terms, 2 negative, 1 positive, all three are the same. So what you've got is that something is non-negative, and that something is FF minus FG GF over GG. All right, so now you multiply both sides by GG, and you get 0 less than or equal to FF minus FG GF, and I forgot to stick in the GG, so GG. And so that is equivalent to, that's the same thing as FF times GG is greater than or equal to FG times GF. And of course, this is the Schwarz inequality. So this is that. In other words, this is the same thing as FG F squared. This is the complex boundary. Yeah.
I'm a little confused on why you
So am I.
why you set lambda to GF.
Oh, that's the whole trick. I mean, you can set lambda to anything you want, and then you're just in a quagmire. This is the clever choice of lambda. Good question. Let me get you a candy. Good catch, good catch. Okay, so that's the Schwarz inequality, and this thing is often written by taking the square root. If you take the square root, you get norm of F, norm of G, greater than or equal to absolute value of the inner product of F of G. So that's another way of, that probably is one of the common ways of writing the Schwarz inequality. All right, some examples of the Schwarz inequality are the dot product of two vectors, r dot r, big R dot big R, greater than or equal to r dot big R squared, and in fact, this thing r dot big R squared itself is r squared big R squared cosine squared the angle between them. If you have n vectors, then you have x dot x times, what do they call it? Y dot y is greater than or equal to x dot y squared, which is x squared y squared cosine squared theta. Here, when I say x squared, I mean the inner product of x with itself. This is the real Euclidean vector space. Any questions? All right. Now, one of the homework problems, not due next Thursday, but probably due a week or two after that, is that this Schwarz inequality for two real vectors, which I just wrote down, it implies an inequality that's seemingly unrelated. Namely, this one by the way of addition. And of course, this is another famous Schwarz inequality, namely that the length of two vectors is greater than the length, the sum of the lengths of two vectors is greater than the length of the sum of the two vectors. Where are we on time? Now, of course, all these things also hold for complex vector spaces. So you can have the complex vector spaces, you have something like u star dot u, v star dot v is greater than or equal to u star dot v absolute value squared, which you can also say is I don't know, if you'll let me write it that way, I'll write the other one the other way. U bar dot v. Cosine squared theta. In other words, this is u bar dot u. And it implies that the length of the sum of the lengths of the two complex vectors is greater than or equal to the length of the sum of the two complex vectors. And as yet another example, I did the case that's rather close to quantum mechanics, namely the inner product being an integral of f star g from a to b. In that vector space, we get another Schwarz inequality, integral a to b dx f of x squared times integral a to b dx g of x squared. So this is norm of x squared, norm of b squared, greater than or equal to absolute value a to b dx f star x gx squared. So that's another example of the Schwarz inequality. All right, so any questions before we launch on from here? All right, the next topic is also important. So in the first lecture on Tuesday, I covered very rapidly a lot of things that I assumed you had in high school or college. And today I'm covering things that you may also have had, but you probably didn't have, you may not have had in sufficient detail or generality or rigor. So, or maybe you had them and it was all fine, but you've forgotten them. I've forgotten everything. The next topic is one of these that's important. It's linear independence, completeness, and linear dependence. These are concepts that I particularly like because there's a certain cleanness about them. A certain simplicity, and yet they're extremely important mathematically. Okay, so you have a set of n vectors, v1 up to v capital N. We say it's linearly dependent if, can I just say TE for there exists? Is that okay? There exists constants C1 to Cn, not all zero. Such that 0 is equal to C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. So it's a very simple concept, or it's simple to state. So your vectors are linearly dependent if you can find a linear combination, if you can find n numbers, not all of them 0, such that when you multiply each of the numbers times each of the vectors, you get 0. The 0 vector. So for instance, Suppose we just had two vectors. Suppose these two vectors were pointing in the same directions, they were parallel. Okay. So clearly, if you have the two vectors parallel, you can take, and if the two vectors are this vector and then the arm, all right, what you do is you take 1 times the arm plus -5 times the short one, and you get 0. 1 is non-zero, -5 is non-zero, so these two are linearly dependent. More generally, if you have, say, imagine vectors as arrows on the floor. So these would be vectors in a two-dimensional space. You can have 2 of them to be linearly dependent if they're not parallel or anti-parallel, but you can't have 3 of them, because then they'd be linearly dependent. And, all right. Okay, so that's linear dependence. There's another closely related definition. A set of n vectors, v1, vn, linearly independent. Well, this is a very simple definition.
If it's not linearly dependent.
The vectors are linearly independent if they're not linearly dependent. And so that's mathematics
Proof.com.
is always at least consistent. Maybe irrelevant, but consistent. Okay. All right. Next concept. Suppose you have some linearly independent vectors in a vector space. The set is maximal if you can't add another and keep the set to be linearly independent. Okay. So in other words, the set VI is linearly independent, and it's also maximal if you take any other vector in the space, add it to the set VI, and here I mean all of the VI's, n vectors here. This is linearly dependent. Okay, so you add any vector in the space, well, obviously you add any vector space that's not already one of these, or parallel to one of these, you get 0.
Would that mean that that set spans the space?
Yes. Good. Actually, the way I wrote it in the book is actually correct now that I think of you don't need to add anything else. In other words, you add any vector in the space to the set, it's linearly dependent. Obviously, if you had 2 copies of V1, be automatically linearly dependent because you would satisfy, you could just write down 0 equals V1 minus V1. You're done. So the idea is you have a set that's linearly independent. It's maximal. If you try to add anything else, you get a linearly dependent set. All right, and as was pointed out, in fact, you must get I've got to give you credit for that here. I guess it's a question multiplied by -1. An inverse question. What he said. All right. Okay, suppose you have a maximal set of linearly independent vectors. You can represent any vector. In other words, you can represent any vector as u is equal to u1 v1 plus u2 v2 plus u, what did I say? How many n's capital? So the point is that your maximal set of linearly independent vectors can represent any vector, for example, any vector in the space, for example, u. And the point is that the set u V1, Vn is linearly dependent. Linearly dependent means that we can write 0 equals C0u plus C1 V1 plus dot 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 plus C capital N. V capital N equals 0. But now we can do this with C0 non-zero, because if C0 was 0, this would be the statement that the V's are linearly dependent. So C0 is non-zero, and then we write U is equal to minus 1 over C0 times C1 V1 plus Cn Vn. So now we've represented an arbitrary vector in terms of a maximal set of linearly independent vectors. So that's the notion of spanning the space. You can represent any vector by it. And we also say it provides a basis. So a maximal set of linearly independent vectors in a vector space forms a basis for that set, that space. And a basis, of course, is something such that you can write any vector in the space as a linear combination of the basis vectors, which then have to be maximally linearly independent. All right, the next topic is the dimension of a vector space, and I'm sure you can sniff out what the answer is. Namely, the dimension of a vector space is just the number of vectors in a maximal linearly independent set in that space, or the number of vectors in the basis. But if we're going to prove that, we need space somewhere I can write maybe I'll erase that stuff there. Trouble is, it's closely related to what I'm talking about. All right, I'll work on this. Let's just get rid of all this. All right, let's see if we can get through this before we run out of time, which is 4 minutes. Okay. So we've got V1 to Vn and W1 to Wm. And we're imagining, suppose we have two maximal linearly independent sets of vectors in some space. What do I call the space? S. S for space. Now what I want to show is then n has to equal m. So the first thing is to show that that the definition I just gave of the dimension of the space makes sense, namely that you can't have two maximal sets with different numbers of vectors in them. Okay. So say m is less than n. The w's are complete. So we can write any vi as a sum j equals 1 to m aj I wj. So the I is the coefficient for this vector, j is the coefficient that goes with the basis vector, and you sum over the m of them, you can write any one that way. So that's because the w's are complete. And now we can think of these A's. These A's are a matrix, but we can think of them as a bunch of vectors. And what I'm going to do is I'm going to say that C is a vector well, little c. All right, no, AJ, first of all, AJ. AJ is the vector that has components AIJ. So this is A1J, and how many components are there? It has as many components as the first index, and the first index is n components. So I is the number is n, j goes to m, and I'm going to take the matrix elements of the jth column of this matrix and call the vector aj. And there are m of these, so there are m different vectors, m aj's, and there are maj's because the index j goes over these m indices. All right, but on the other hand, n is bigger than m, so you can always find a vector c that's orthogonal to all of the aj's. So C is a vector with components C1 up to C big N. And so you can find a vector C such that the sum I equals 1 to big N of Ci Aij equals 0. And that's simply because if you have, these are m, I'm losing track of, these are m vectors, and you can find, all right, let me just give an example. Suppose you're in 2 space, the vector's on this table, then you can find always a vector that's orthogonal to all the vectors on that table. It's just, say, this vector, because it's perpendicular to all of them. And that's because it's in a bigger space, because n is bigger than m. So you find this vector C is orthogonal to all the aj's. This is the statement that, C dot, this is C dot aj equals 0. And there are capital M vectors there, and they all have capital N components, and so these are 3 vectors, but they're all lying on the table, so they're orthogonal to that. Okay, so that statement then is, we can arrange that Ci, Vi, this linear combination, I equals 1 to big N. Well, what are the VI's? The VI's are these guys. So that is sum on N on I, sum on J to M, Ci, Aij, Wj equals 0. So I use this equation together with that equation. I get Ci, Vi equals 0, but the Ci are not all 0, and consequently, I've shown that the V's were linearly dependent. So in other words, if we have 2 maximal sets, one has more vectors than the other, then this one, the one with more vectors, has to be linearly dependent. I'm sorry, yeah, it has to be linearly dependent, so it wasn't a maximal set of linearly independent vectors. So what we get is that n can't be bigger than m, and consequently you reverse the argument and you show that m can't be bigger than n, and so m and n have to be equal, and we're out of time. And so that's how you define the dimension of the vector space. It's a set of m, the number of vectors in a maximal linearly independent